The topic of this film is universal motors and their basic investigation and theory will be presented. And what are given in this tutoring movie is properties and applications of the universal motors will be summarized. And as an illustration, a universal motor from the market is also examined. Actually, this is the stuff that we are talking about. That's a universal motor, one of the most inexpensive ones in the market. In order to fully understand the topics presented in this movie, you should have sufficient knowledge about electric motors and parts. And the parts include rotor, stator, brushes, windings, etc. Electromechanical energy conversion, especially the force or torque induced by means of electrical power input. Torque speed characteristics of motors, of course, and equivalent circuit representation of especially series, so-called series motors. So let's return back to our basics. The definition of universal motor can be given in the following slide, but bear in mind that they are also called AC, alternating current series motors, or commutated series wound motors as well. So what's a universal motor? It's a single phase series motor. It's a series motor, and in alternating current wise, it's single phase. It's also capable of running on DC as well, so you can excite the motor both AC and DC with similar characteristics are obtained. Those are called universal motors. So excitation is arbitrary, independent of the characteristics of independent of the excitation. So the universal indicates that such a motor can run both on AC or DC. Now what's inside this motor? Okay, this is a universal motor with rotating shaft and some connections, electrical input, okay, and ground, of course, one of them. So if you remove those two screws, we can take this cap out and we will see structure similar to that. And this is the shaft. These are the stator windings. And also this one is the other pole of the stator. And this is rotor, so it rotates. So the magnetic core material of the rotor is shown, and there are some copper conductors. Those are commutator conductors. And not shown here, but these two are carbon brushes which conduct electricity from outside to the rotor windings. So its equivalent circuit is, we have supply, we have field, and we have armature. Armature is the rotating part, which is rotor. Field is the stator part. And so induced current, induced voltages appear on these rotor windings, and these black rectangles represent the brushes. And the operation of the universal motor is like a series machine. Theory of operation of a universal motor is quite similar to the DC series motors. However, DC series motors do not operate well on AC because of poor efficiency and low power factor. A universal motor is designed in a way to reduce these disadvantages. armature and field are in series. The current is the same through them, and there is no time lag and phase shift in magnetic fields of stator and rotor. Runaway speeds can damage the DC motors, DC series motors, when no load is connected. So this situation is usually avoided connected a load. So in universal motors, always connect a load before the operation. Never operate the motor unloaded. So why universal motors are not used in shunt connection? A question may arise. The answer is, under AC operation, there exists a high reactance which will reduce the current through the shunt field. A lower field current will have weaker magnetic field and fail to obtain necessary torque to start the motor. So in order to start or apply high torque, we use series motor or universal motor. In that motor, in like on all the machines, we observe armature reaction, so-called, according to the rotor current, there is a reactive rotor magnetic field which distorts the field in the motor. The armature reaction is greater in a universal motor than the DC motor with same ratings. This is due to the large number of armature conductors and armature magnetomotive force. Compensating windings are almost always used to reduce the effects. The compensating windings may be wired, conductive or inductive. So compensating windings are in series with the armature current, which is the same as field current, and contributes to the net field of the machine. So if those windings are not present, the armature field distorts the normal field, but compensating windings makes them reordered again. What happens to torque speed characteristics of the universal motor in general? They are basically series wound rotors, therefore they respond to increasing loads by slowing down. Slowing down means that the current increases and torque rises in proportion to the current, since the same current is flowing in both armature and field. So field flux equals to or directly proportional to the field current, and torque is directly proportional to the field flux and armature current. Since field and armature currents are equal, since they are in series, torque is directly proportional to the square of the current of the motor. These K's are geometrical constants related to field and motor respectively. For example, we have a basic verbal question of show that the time average torque of universal motor under AC excitation is proportional to the square of the root mean square value of the current in the armature, which was taken from one of the textbooks related to this material. And the solution for that problem is relatively straightforward. In the one of the previous slides, we have shown that torque is directly proportional with the armature current, square of the armature current, and the average torque is time average over one period of this current value. And if you take this integral, you can find that the average current is again, the average torque, is again directly proportional to the square of the armature current or field current. They are the same. This also confirms that universal motors have similar characteristics under AC and DC excitation. So in AC, my RMS current has the same effect as my direct current in DC application. So never consider the peak value. In the average, they are the same. In a universal motor, full load operating speeds are usually in the range of, say, 4,000 to 16,000 RPMs. Because of the high speed of the motors, they have higher developed horsepower per weight of the tool ratio compared to other AC motors. This makes them particularly applicable for portable tools since they are lightweight. And the torque speed characteristics of similar machines are given as above. So for the same torque, the speed is slightly lower than DC counterpart in compensated type, and in non-compensated this gap is even larger. So in AC, pulsating effects and reactance, power loss, etc. will slightly degrade the torque speed characteristics, and this is given in one of the internet links. So since speed is varying, we need to regulate it. Speed controls are available on many devices that use universal motors. This might be accomplished by putting a resistance in series with the series field and armature, reducing the voltage to the motor using a variable or tapped transformer, or we can use silicon control rectifiers to adjust the average level of the AC. So schematically they are given like this. We can place a rheostat or variable potentiometer in series with the field and armature, or sender tapped capacitor to adjust the input voltage, or we can have discrete adjustments to connect different poles in the machine. So this machine has different internal windings than the first two ones, or the alternating current or supply voltage can be controlled by this power electronic circuit. This is like a voltage chopper, which can be explained in another slide. So these are basic methods of controlling the speed of universal motors. So torque times speed gives the mechanical power, or voltage times armature current also gives electrical power. So what can we say about the power and efficiency of this motor? Universal motors do have some losses like other motors. Copper losses are in the windings, and they are reduced by using larger diameter wire, so that resistance of the wire drops. So as resistance power loss I square R also drops. Hysteresis losses are limited by annealing special silicon steel, so using better magnetic core material, and we use lamination to reduce eddy current losses in those machines as well. However, the efficiency of universal motors are fairly low. They range about 30% in small motors to 75% for larger types. Universal motors are commonly used in the portable machines, requiring high power outputs. Their maintenance are inexpensive, easier, but high speed creates lots of friction between brushes, and the brushes will wear out fast, so they need maintenance. So what can we say about applying AC and DC excitation? Starting torque is determined by the current that flows through the armature and field windings. Due to inductive reactance of these windings, the alternating current starting current will always be less than DC starting current. Why? Because we have reactive. So AC excitation has softer start, so-called softer start. Consequently, starting torque on AC power will be lower than DC. Universal motors are often found in range less than 1000 watts. For example, this motor has a rating of 100 watts. High speed makes them useful for appliances such as kitchen blenders, home appliances, etc. They are commonly used in portable power tools, drills, sanders, etc. Some combustion engines also use universal motors as their starting motors. So that's about it. This was a summary of universal motor topic, and information presented in the slides are taken out from either textbooks or internet resources, as well as personal experiences in the field. The preliminary slide preparation was made by Mr. Ozcan Açık, and finalization and narration and film presentation were made by myself, and with the infrastructure of my university. And I would like to be happy to receive your comments about this film or any other information giving film that may be requested. Thank you for watching.